Hello guys, my name is Ismail Kamal. I'm gonna be showing my project, the first aerodynamics fluid project. So for this project, it's about a simulation of a 2D cylinder and ANSYS. We got a couple of cases. We got 3 cases: envisaged flow, laminar flow, and turbulent flow with different Reynolds numbers. The velocity is 10 meters per second. Diameter of this cylinder is 1 meter. And we have to compute all these uh, questions here that they're asking for. They're asking for the velocity and the pressure contour, the streamline patterns. They're asking for a plot of the pressure coefficient and the velocity distribution over the surface. And for each case, we also have to determine the drag and lift coefficient. And for the last case, we're only dealing with the laminar case, and we have to have 2 rotation cylinders, both clockwise 20 radians and another one 40 radians. So for this project over here, I'm gonna be showing the geometry. Okay, so we got this body, right? I'm gonna be showing how I want to show my sketching. Okay, so I use this line, right? So I use this line properly over here to draw a line, draw 4 lines and a small circle over there of radius of a diameter of 1 meter, right? And then I had to go to the mesh part of this project, and I'm going to be showing you the mesh part. So I named this part here the velocity inlet, this part here the pressure outlet, symmetry here in the top, and for that small circle, it's that cylinder wall, right? After I did that, I generated my mesh. I'm not going to be showing that, but I generated my mesh, and then it took me to the last part, which is the setup part, right? The setup part, it takes us to this page here. That's going to be my ANSYS page, right? So this is my ANSYS over here. And I'm going to be showing how to do for this one over here. I'm just going to be showing let's see which one. Okay, for this one, I already did the turbulent flow, so I'm going to be showing the turbulent flow case. So it's going to be the third case. So for the third case, I turned on my energy. It was on, so the energy equation is on. And for general, I have the type here. It's pressure base and velocity of out formulation is absolute, not relative. The time is steady, not transient. So it's a steady time state. And my radiation heat exchanger species are all off. And then we're gonna go to this part, which is the material part. So for the fluid, we're working with air. Okay. So for fluid, we're working with air. I used a density of 1.22 kilogram over meter cubed. So we know that the equation for Reynolds number is density times the velocity times diameter divided by the viscosity, right? So if I'm using my calculator right now, the velocity is 2 meters per second, the diameter is 1, the density is 1.22, and the viscosity is 1.525 times 10. So then again, 5. I'm getting 80,000. That's my number for Reynolds number. So after that, I had to obviously edit it by changing the viscosity or the density. So I had to change that. And then for my solids, it's the same. We're gonna go to the cell zone condition. I had to change this part too. So for this part, I had to go over here and make sure that the density and the viscosity is the same one that I use for the fluid that I have here, which is air. So apply, close. For the boundary condition, we're gonna have to deal with each one of these. So for the cylinder wall, there's for the special case, this case over here, we had to change it from a stationary cylinder to a moving cylinder. So if we want to change that, I can go over it when I'm doing my laminar flow. Since I'm doing turbulent, I'm not going to be applying it, but we just go over here, moving a wall, not translation. It's going to be rotational, and then we change the speed. See, you can already see the speed that I use for the last case of my laminar flow, which is 40 radian per second clockwise. But for this case 3, turbulent flow, I'm just going to be dealing with a stationary cylinder. So I'm just going to apply close, go into the interior surface body, nothing's going on. The pressure outlet, it should be 0, right? Right here. That's going to be my pressure, which is basically your, it's going to be also normal to the boundary. Apply close. For the symmetry, nothing is showing here. The symmetry for the top, nothing is showing here. For my velocity inlet, I had to change the velocity, the magnitude of my velocity, right? So reference is absolute, not relative. The magnitude should be normal to the boundary, right? And the velocity, like the projects told us, it should be 10 meters per second. So that's why I did over here. The velocity is 10 meters per second. Apply close. Okay. Also, for my reference value, very important that we change these reference values so we can see that the area is 1 meter per square, which makes sense. See, we had to change this density, and we also had to change the viscosity and make sure that the reference values are correspondent, are the same as the one that we have for our problem. And the velocity, it should be 10 meter per second, right? And then we go over here to methods, the scheme, like Dr. Osbey, he changed it to simple, not coupled. Some people use coupled, but I use simple. For the pressure, I was going to be using sender, but Dr. Osbey told us to use Presto, so I'm using that. I don't know the difference, honestly. I think it's going to be accurate or something, but I'm not sure. For the initialization, I click this. We go to more settings, and the number of iterations that it shows here was 35. I think it was the same as the one that Dr. Osbey had in his tutorial. Click OK, and then we just need to run the calculations. So for the first and the second case, I use 1000 for my number of iterations, but for my turbulent case, I was not going to be waiting for 1000 number of iterations, and I'm pretty sure it converges after like 500 or 400. So I use 600. After I use that, I click and calculate. I already calculated it, so I'm not going to be running this calculation right now. After you finish calculating, you can just go to your solution over here, or you can go look at your results. So I'm just gonna go ahead and click on solution and see if it's gonna be preparing my mesh. Okay, I'm assuming I have to like run this calculation again. Yeah, I have to run it because I already, yeah, I have to initialize it first. Initialize. So the initializing is done, and then I have to run this calculation. It's gonna take me a little bit of, actually I can just, I'm just gonna be stopping this calculation because I already made it, right? So yeah, I'm gonna be looking at my contours right now and see if I can compare them to the one that I have, because I already have all the results for all the uh, contours for the velocity and uh, the pressure or the streamlines, and then I have this pressure coefficient and the velocity magnitude. I also added the drag force, lift force, drag coefficient, lift coefficient. I'm pretty sure Dr. Osbe only asks us for the drag coefficient and the lift coefficient. I used the total for those values, but I also added the drag force and the lift force. I put them in a table over here. So since I already did the calculations, I'm going to show you my pressure. Let's start with the velocity contour. So I'm going to compute, say display. So this is my contour, my velocity contour for the case number 3, I'm assuming. Yeah. So I didn't run the calculation over here. That's why it's not showing the same contour. But this is how the contour should look like for my viscous turbulent flow, right? This is my velocity. This is my pressure contour. I'm also going to be showing my pressure contour. You go over here, contours of what? Pressure. You can look at your static pressure, absolute pressure, total pressure. I'm looking at my static pressure. And I'm also choosing all these parts, compute, save display, and you can look at your pressure contour over here. It's a little bit different, like I said, just because of my calculation, but this is how it should look like for the turbulent flow, because I did it like 4 times just to make sure that I'm getting like similar results. But this is the right result that I should be getting for the velocity and the pressure contour for a turbulent flow. What else we got here? I'm showing my streamline. Yeah, I'm not going to be showing my streamline until I do the results, but let me show you the pressure and the velocity plots. So for that, we go to plots, XY plots. I already have like 6 of them over here, have them saved. So we're gonna go to the velocity plot, and I'm not doing all of these, I'm just doing the cylinder wall. So save plot, and you can see that the velocity magnitude should be 0. I'm also going to be showing my pressure plot. So pressure, not static pressure, pressure coefficient for the cylinder wall, save plot, and you can see your plot over here. Okay. Excuse me. See, like you can see, I already put those plots for the turbulent flow, right? And finally, we can look at our the last part of our problem, determine the drag and lift coefficient. So Dr. Osbe only asked us to find the drag and lift coefficient. I found those, and I also added the drag and lift forces. To find those forces or those coefficients, we go to reports, forces. So for the drag force, we should have x equal to 1 and y equal to 0, cylinder wall, print. I'm sorry, print, right? So print, and then you can look at your drag force. So this is the total drag force, and this is your total drag coefficient. For our lift coefficient, our x should be 0, our y should be 1, print, and we can look at our total lift force and our total lift coefficient. What else we have for the last part? Dr. Osbim is, oh yeah, I didn't show the streamlines. So for the streamlines, we gotta go to results. And then it's gonna show us our posts, CFD posts, right? So for the CFD posts, this is what's gonna be popping, this page. We can see here that it's loading. So loading. Okay. So I'm just gonna delete the streamline that's showing just so I can show. So you go to insert streamline, streamline 1. It's gonna be our surface streamline. For this, Dr. Osbey shows the symmetry.1 surface, apply. I don't know, it's not showing me. I'm just gonna delete it again. Go to my streamline over here. Anyhow, it should be showing the velocity streamline. I'm just gonna be showing it over here, but that's how you should be finding the velocity streamline. So after this, okay, so now I'm going to be showing how to change your setup for the first and the third case. So for the first case, we have first case is envisioned flow. So for that, I'm going to close this page, my CFD post. So for that, I did turn off my energy, right? I also went over here to change it to envision flow. Clicked OK. For my fluid, if we can see, it's gonna have the same density, right? So same density is applied. For my they're not letting me change the viscosity for the first case or any other property. So the only thing that I can change is the density. For the boundary conditions, what can we change? So if we go to the cylinder wall, we can't change the rotation, the speed of rotation, the rotating cylinder. We can't change that. Pressure outlet should be the same, right? And for the velocity inlet, obviously we need to keep the same velocity magnitude. After we change all that setup, and we make sure that if we go to methods, the scheme and the pressure should be the same. We just need to initialize, and I used the hybrid initialization, more settings, 35 uh, iteration, and then I ran my calculation. So after I ran my calculation, this is what I got for the first case for the envisioned flow. So this is my velocity contour, this is my pressure contour, this is the streamline pattern that for the stationary cylinder it looks perfect here, right? My pressure coefficient, we can see that it's in between -3 and 1. That's our minimum and max pressure coefficient. And this is my velocity magnitude. So the velocity magnitude, the max should be 2 times our velocity. The velocity was 10, so we're just multiplying that by 2, and we can see that our maximum velocity is 20 meter per second, right? Uh, by the way, I'm just gonna make sure that you guys know that the drag forces, lift force, drag coefficient, lift coefficient, I'm using the total values that the program is giving me, the ANSYS is giving me. Okay. And for the second case, what I did is I turned my energy on, right? I only turned my energy off for the first case, but for the second and my third case, I turned the energy on. So we go to viscous, laminar, press OK, and now I have to change my properties here. So what I did is I used 1 kilogram over meter cubed for my density, but for my viscosity, I use 6.6667 E negative 0.5. So I'm just gonna click change create, and then I'm just gonna show you guys that I'm getting that Reynolds number that was asked here, which is 150,000. Okay, so if I use my Reynolds equation, my Reynolds formula, so I have that velocity of 10, density of 1, the diameter of 1, divided by our viscosity, which is 6.667 times 10 to the negative 5. So this is what I'm getting here. I'm getting 14999, which is basically 150,000. So after that, I made sure that my property is changed here, is changed, and then I made sure that my reference values are changed. See, it's not changed here, so I gotta change it. I had to change it to 6.6667 E negative 0.5, and for my density I got 1 here. Okay, and then my methods, make sure it's still the same, and then all I need to do is do my initialization and then run my calculation, and then finally we can get my velocity and pressure contour for this case, the laminar case. So I got this velocity contour, this is my pressure contour, this is my streamlines, and finally I got these two plots, pressure coefficient and velocity, the total drag lift and drag lift coefficient, I got them here. And yeah, so for the last part, I had to use a rotating cylinder. The first one was 20 radians per second counterclockwise. I mean clockwise, yeah, clockwise for the negative. Yeah, clockwise for the negative, and this is what I got for my velocity and my pressure contour. And those, you can see that the pressure contour was very, very high for the 20 radian per second clockwise. My streamlines are here. Velocity and pressure coefficient plots are here. For the negative 40 radian per second. This is what I got for my velocity contour, pressure contour, streamline, the 2 plus. We can see that there's a pattern in our velocity magnitude. It stays 0. And this is my table for the dragon lift. So yeah, thank you guys very much for watching this video, if anyone is watching it, honestly. But I'm just doing what I need to do to make sure that I do good in this class. And yeah, thank you very much. Stop recording.